We'll just start on a new chapter today. This chapter is still talking about forces, but this time is more on the effect of force in deforming a solid, hence the chapter name being Deformation of Solids. You know that whenever you apply a force onto an object, or specifically a solid, it has the ability to deform the object, right? It can either stretch the object or it can either compress the object. So when you apply a force onto an object, causing it to deform, there are two types of force: tensile force and compressive force. Okay, now tensile force is a force that you apply at both ends of the material, like this. You are pulling the material at both ends, causing an increase in length. Okay, so we will say that the material is under tension. This is what tensile force is. You pull the material at both ends, causing an increase in length. The material is said to be under tension. Now, compressive force is the direct opposite of tensile force. Rather than pulling the material apart, you're pushing the material together at both ends, causing a decrease in length. So when you apply a force pushing both ends of the material together, what will happen here is that you are actually trying to cause the length to decrease. So this is what compressive force does. The material will be said to be under compression. Okay, wait. Hi, Regan, you just joined? Yeah, I just saw your message. You're having lunch. No worries, we just started, I think, a minute or so. The lesson is recorded, so you didn't really miss much. Okay, so, okay, so we'll just continue. Right, so tensile force, it pulls the material at both ends, causing an increase in length. Material is under tension. Compressive force, it pushes the material at both ends, resulting in a decrease in length. So the material is called as under compression. All right, so these two forces, you need to know a bit of what they do. All right, now a material can also experience both tension and compression at the same time. That is when the material is bent. If, say, for example, I accidentally closed the share screen. Now, say, for example, if you have a beam like this, originally the beam is straight. Okay, this is your beam that is straight. If you were to somehow apply a force F, pushing the beam down, and we say that the beam is supported here by something, maybe 2 blocks of wood. If you have a beam here and then you apply a force downwards, the beam will bend in a manner similar to this. Okay, so in cases where you subject a material or solid to a force like this, causing it to bend, the material will actually experience both tension and compression. What we will normally tell you is that the bottom surface is actually being stretched. So because the bottom surface is being stretched, there's an increase in length. The material, that part of your beam is actually under tension, but the top surface is being pushed together, causing a decrease in length. Thus, the material at the top surface is under compression. You can imagine that if that beam is bent like this, the bottom portion is being stretched apart, whereas the top portion is being squashed together. That's why here we will say that this is tension, and then this one here is compression. Okay, so a material can have both compression and tension at the same time if you apply a force like this. The ones that you see here is more like a case, the ones that you're seeing here is more like a case where the beam is like this. It's more like a case where the beam is like this, and then you apply a force like this. This one, you apply a force along the axis of the beam. But this one here, you're not applying the force along the axis of the beam, you're applying a force perpendicular to the beam. Okay, so the same force can cause different effects here, compression, tension, or both at the same time. All right, and then you look at the bottom portion here. A thin rod can be bent more than a thick rod without breaking. Now, if you have two different rods, or rather two different wires in real life, I have a wire that looks like this, and then I have another wire that is much thicker. So in general, when you try to bend this thin rod versus this thick rod, what you will notice is that the thin rod can actually be bent more compared to the thick rod. The thick rod will actually break first. If you take two different rods of the same material, the thinner one, you can actually bend it a lot more until it looks like this. But the thick one, maybe somewhere along the way you bend it, it suddenly breaks in the middle. So why is it that thin rod can actually bend more than a thick rod? Now, the idea is this: if you were to bend the rods for the same angle, maybe I better just show it as this. If you were to bend it for the same angle theta, like this, say maybe this one is 45 degrees, and then this one here is 45 degrees, what you will see is that in terms of this portion here, this surface here, tends to extend more. Therefore, it's under higher tension. It'll be easier to see it as this. You see, if I had a sector like this, all right, and I tell you two different lengths. This one here, I give you two different lengths. This length here and this length here. This length here is obviously more than this length. Okay, because you see, when you are talking about thicker rod, it's like you having something a bit more like this. Okay, so if you have a thicker rod, this length here would definitely be more than this length here. And then likewise, this length here will definitely be more than this length here. Maybe I better just show it a different way. Let me just redraw it properly for you. If I give you three different lengths, L3, L2, L1. L3 more than L2 more than L1. Okay, so this one is if the rod becomes thicker. So the idea here is that if you have a thin rod, which is this one, and a thick rod, you bend it by the same angle theta, let's say 45 degrees here. This thick rod tends to have a larger change in length. Okay, this rod here at this surface here, it will tend to extend more. So it will be under higher tension. All right. And because it experiences higher tension, it tends to reach breaking force first. Therefore, it breaks first. Right? All materials will break after a certain force. So if I tell you that the breaking force is 100 Newton, if I talk about the thin rod, I bend it at angle 45 degrees, maybe the extension here is just going to be 60 Newton. But for the thick rod, because it's thicker, I bend it for the same angle, this surface will extend more. It will have higher tension, so the force here will probably be 95 Newton. Okay, it will definitely be larger than the ones here. Okay, so it tends to break faster. It will break first. Okay, This is an old past year question that they asked last time, long time ago, but they seldom ask it nowadays. This one in the last 10 years, they've not asked. I think before 2010, they asked once. So I just teach you what this means now. Right, so this is tension and compression. Okay, now we go to the main part, which is this one. This one is talking about Hooke's law again. Now, Hooke's law, you guys always remember it as something like this. F equals to Kx. And you guys always remember it as being related to spring. So we are going to talk more about this right now. Now, if you want to investigate the extension of a spring under a tensile force, under the action of a pulling force, you will normally use an apparatus that looks like this, where you have a spring and then you attach a load onto the spring so that the spring extends. Then what you're interested to know is that how much would the spring extend? So for that purpose, you put a ruler here. So when you apply a load here, the spring extends, it will extend by a certain amount x. What you will do is that you will take the original length here, you will note down the original length here, and then you note down the final length here. The difference between these two will give you your extension. So what you want to do now is that you want to vary the load and then you want to find the extension. So maybe your F is 10 Newton, then going to 20 Newton, 30 Newton, 40 Newton, and so on. And then from there, you find the corresponding extension. All right. So what you want to do from there is that you want to plot a graph of force versus extension. So when you plot a graph of force versus extension, typically for spring, you will tend to see something that looks like this. Let's just focus on the solid line first. All right. So this is an apparatus that you use to measure the extension of a spring under load, from which you can deduce something called Hooke's law. All right. So let's look at the graph. What does it tell us? If you look from O to A, which is from here to here, you tend to see a straight line that passes through the origin. Now, when you have a straight line that passes through the origin, it tells you that the extension x is directly proportional to the applied force, meaning to say F is directly proportional to x, it means this, okay? When F is directly proportional to x, that means Hooke's law is obeyed. What you learn is that Hooke's law states that within the limit of proportionality, the extension produced in a material or spring is directly proportional to the load applied. Okay, this is what Hooke's law actually is. If you're asked to define Hooke's law, this is the definition. In equation form, it is this. All right. Now it's from this form of the equation that you eventually get F equals to Kx. You remember that in maths, if you want to get rid of your proportionality sign, you will normally introduce a constant. Okay. You will normally introduce a constant. This constant here is known as your spring constant. Okay. Since F is directly proportional to X, introducing the spring constant K, your equation thus becomes this. Okay, and this is Hooke's law equation. All right. You want to get rid of the proportionality sign, you just introduce a constant. That's where you get your spring constant. Now, the spring constant is sometimes known as the constant of proportionality. All right. Now, what is useful about spring constant is that it tells us the stiffness of the spring. All right. Stiffness is a material's opposition to changes in its shape or size. Think of it this way. If the material is stiffer, it's harder to deform. If the material is less stiff, it's easier to deform. Okay. So spring constant is a measure of the stiffness. You will expect that the higher the spring constant, the harder it is for you to deform the material. Okay. Now, spring constant is expressed as force per unit extension. All right. it is force per unit extension carrying the units of Newton per meter, because F equals to Kx, K is F over X. Force has the unit of Newton, extension has the unit of meter. So you get Newton per meter. All right. So it will tell you how much force is required to stretch a spring to a given extension. The larger the spring constant, the larger the force to stretch the spring. Therefore, it is harder to deform because you need to use more force now to extend it. All right. Okay, so we cover up to this part here from O to A. Now, if you look specifically at point A, and then after that, at point A, the graph will stop being a straight line. After that point, you will notice that it no longer is a straight line, okay? At this point here, force is not directly proportional to extension. I wrote extension as x, right? At this point here, force is no longer not directly proportional to x. Okay, so this point here is where Hooke's law is no longer obeyed. Okay, it's only at this region here where Hooke's law is obeyed. Only the straight line portion. You see this part here is where your graph is a straight line, right? This part of your graph, which is a straight line, tells you that force is directly proportional to extension. Therefore, Hooke's law is obeyed. Okay, so only this part here is where Hooke's law is obeyed. Okay, it's indicated in your graph here. Only up to this part, Hooke's law is obeyed. But then after that, Hooke's law is no longer obeyed. If you want to, you can probably just write it here somewhere like this. Also, Hooke's law not obeyed. Okay. So that point there, point A, is actually what you know as the limit of proportionality. Okay. So I need to drop off a few things. That point A, where your graph ceases to be a straight line, is the limit of proportionality. It is the point to which Hooke's law is obeyed. Okay, it is actually this point here. All right, this point is your limit of proportionality. Okay, Hooke's law is obeyed up to this point. Anything after that, Hooke's law is no longer obeyed because you see that the graph is no longer a straight line. Okay, so this one here, f is not directly proportional to x. Hooke's law no longer obeyed. Maybe if you want to, you can say that because graph is no longer a straight line. Okay, because graph is not a straight line, we cannot say that f is directly proportional to x. F is not directly proportional to x. Therefore, Hooke's law is no longer obeyed. Okay, so that one covers proportionality. Now, when you apply a load onto a spring, you know that it will tend to extend. But what happens when you remove the load? You will understand that if you remove the load, the spring will go back to its original length. And then in some cases, if you overdo it, meaning to say you apply too much load, the spring will go back, but it doesn't go back to the original length, right? So there is a point that will tell you whether the spring will go back to the original length or whether it doesn't. So that one is actually indicated by this point here, point B. I'm just going to clear off this part. is actually indicated by this point here, point B. Okay, so what we will tell you is that removing the load anywhere before point B will cause the spring to return to its original length. You won't have any permanent deformation of your spring. This one is actually known as elastic deformation. Removing the load will cause the material or spring to go back to its original length. Okay, that one is provided you remove the load before point B, before the elastic limit here. Okay, now if you somehow overdo it and then after that you remove the load after point B, you don't remove it before, this time you remove it after point B, or rather beyond point B, the spring will no longer go back to its original length. All right, you will have some permanent extension or permanent deformation to your spring. This is known as plastic deformation. So if you were to remove your load somewhere after your point B, maybe say you remove it here, your spring will go back, but it won't go back to the original length. It will stop back here. Okay, it will generally go back like this and stop here. Now, this one here represents permanent deformation. Okay, it will tell you that once you remove the load and your force becomes zero, you now have some sort of extension here already. There's permanent deformation. So that is plastic deformation here. Okay, so that is what plastic deformation is. All right. Okay, then after that, you go to the next page. Now, elastic deformation, just now I mentioned to you, is elastic deformation returns to original length after deforming force is removed. Plastic deformation does not return to original length or returns some permanent extension when deforming force is removed. If you're asked to define what is elastic and plastic deformation, these are the two definitions that you will tend to use. Okay, right. Now, for the force extension graph, the force extension graph will actually give you your spring constant. It's a measure of your spring constant. Okay, but you need to be careful a bit whether it's a force extension graph or extension force graph, because the gradient will actually tell you something else for the spring constant. What do I mean by that is if you just look at this one, there are two different graphs here, force extension and extension force. Now the gradient is a measure of the spring constant. Okay, when you want to calculate out the gradient, only consider the straight line portion of your graph. Okay, because that's the point, because that's the region where Hooke's law is obeyed. Spring constant is only applicable for a material that obeys Hooke's law. So if you're talking about a material that obeys Hooke's law, it will only apply to the straight line portions of the graph. You do not find the gradient at the curve portion. You must only find the gradient at the straight line portion because that's where Hooke's law is obeyed. All right. So now if you look at the two different force extension graphs, you look at the gradient. What does the gradient actually tell you? The gradient for a force extension graph here is actually equal to K. It's equal to the spring constant itself. Because if you were to find the gradient, it is actually force divided by extension. So you know that force is equals to Kx under Hooke's law. K is therefore F over X. So since you see this F over X here, therefore it's K. So if you have a graph of force versus extension, the gradient is equal to K. But what about if you get a graph of extension versus force. Okay, the axes are now reversed. It's no longer force extension, it's extension force. So the gradient here is actually 1 over k. Because what you can see here is that gradient is actually x over f. Right? When you want to find gradient is the change in the y-axis, which is x here, over the change in the x-axis, which is f here. So therefore it's x over f. So if x over f is 1 over k, right? Because I know that if I talk about 1 over k, it will be x over f. So therefore I get this. Okay. So depending on the graph that you get when you want to find the spring constant, please be careful whether it's a force extension or extension force. Okay. Right. And then if you move to the bottom part here, okay, there is something, this a little bit of maths that I need to go through with you. Now, when we say that a quantity A is directly proportional to quantity B, the emphasis here is directly proportional to B. The graph that you get is always a straight line that passes through the origin. Meaning to say it looks like this. If you were to say that a quantity A is proportional to quantity B without the word directly, the graph is also a straight line, but it won't necessarily start from the origin. What I mean by that is something like this. If I say quantity A is proportional to quantity B, the graph that I could get is something like this. It doesn't start from origin. Okay, why do I need to emphasize this to you? It's because of what Hooke's law said. Hooke's law says that extension is directly proportional to load, meaning to say F is directly proportional to X. Okay, so if I were to give you a graph of say force versus extension like this, I tell you that there are two graphs. One of it looks like this, one of it looks like this. So which of these is actually obeying Hooke's law? We will say that this one is obeying Hooke's law, but this one is not obeying Hooke's law. Okay, because you see it does not start from 0. Force is not directly proportional to X here. Okay, force is not directly proportional to extension. So this one is not telling us that the material obeys Hooke's law. But this one is, because you see it's a straight line graph that passes through the origin. Later in one of the few questions, you will see they will just give you a graph and then ask you whether does this material obey Hooke's law. So the key thing here is that you need to recognize that yes, an object that obeys Hooke's law must have a straight line, but at the same time, it must pass through origin. Just because it's a straight line itself like this does not mean that it obeys Hooke's law. It must pass through the origin because of how Hooke's law is defined, because they say it's directly proportional. So the only way you will get something that obeys Hooke's law is if it's a straight line that passes through origin. Okay, so this is just a bit of maths knowledge that I need to mention to you. Okay, so that is Hooke's law. Okay, now there will be cases where you will be given some spring combinations and then you'll be asked to find out what is the spring stiffness of that system. Okay, I mean, if I just give you a single spring like this and then I give you the value of the load F and then I ask you to find the value of the spring constant K, you can say that F is equals to Kx. K is actually F over X. This will be the spring constant of this spring, this single spring here. But what if your spring is not a single spring? Your spring is a combination of other springs. How then are you going to find the spring constant? That is what this table here below will tell you how. Okay, now you have identical springs with spring constant K that are joined together in 4 different arrangements with the same load applied to each arrangement. Okay, they all have the same load applied to the system. The resulting spring combination has an equivalent spring stiffness of K prime. Okay, this is a different variable. K is not equals to K prime here. Okay, this is a different variable. Assume that the same load applied on a single spring itself produces an extension of E. So what it means is that in my case here, let me clear off everything. What it means here is that for all the same load that is applied here, all these are same load. If I were to apply on the single spring like this here, it will give me an extension of E. Okay, right, that's what this one is trying to tell you. That same load applied onto a single spring like this will give you an extension of E. All right, so let's go through the different spring combinations. Now, if you have springs that are arranged in series, before I go through that, let me just write out some information. Now, if you have springs that are arranged in series, if you want to find the equivalent spring stiffness for this entire system, what you will do is that you will add springs constants together similar to resistances in parallel. Now, this one is something that you will have learned before in IGCSE or SPM. You recall this before. If let's just say I have resistor in series, this one is R1, R2, and R3. The total resistance would be R1 plus R2 plus R3, right? If I have resistor in parallel like this, and we say that it is R1, R2, and R3, the total resistance is going to have an expression that looks like this. 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3, right? It can be rewritten as something like this instead. 1 over R1 plus 1 over R2 plus 1 over R3 power negative 1. Okay, so if you have springs in series, you add up the spring constants like you would resistances in parallel. What I mean by that is that if you look at here, there are 2 springs here. This one has a spring constant of K. This one has a spring constant of K. Because they are arranged in series, if I want to get the equivalent spring stiffness, I treat them like I would resistances in parallel. So the equivalent spring stiffness is 1 over K plus 1 over K power negative 1. Eventually, I'll get the spring stiffness as K over 2. Okay. K here is the spring stiffness of one spring. Okay, you can think of this as the original stiffness. Okay, K prime is actually the resultant spring stiffness. In other words, it's the new stiffness of the system. Okay, so now you see this one, K prime is actually K over 2. Now, this one is saying to you it is half of the original stiffness. So half of the original stiffness here would mean that it's actually easier to deform the spring. You need less force to extend it. Or put it another way, if you apply the same force onto this system, it will tend to extend more. Okay, because you see this one is half K. If I tell you K is say 50 Newton per meter, and I tell you that K prime is now half K, that means it's half of 50, giving you 25 Newton per meter. This will mean that if you want to get 1 meter of extension, you need to apply less force now, half the force. Or put it another way, if you apply the same 50 Newton force, you're getting double the extension now. Okay, so this would make sense because you know that if you have springs in series, it's easier to deform it, not harder. It's easier for you to pull it apart. This one is telling you that story now. Okay, so your spring stiffness is K over 2, but what about your total extension? Now, if I tell you that your load is, maybe I use a different color. Your load here is say F. Okay, this spring here will experience a load F. This spring here will also experience a load F. Okay, now recall that this statement here says that the same load applied on a single spring will produce an extension E. So this will tell you that for this one itself, you will have an extension of E. And then for this second spring here, you again would have an extension of E. So your total extension is actually E plus E, giving you 2E for the system. Okay, so this is how you find the spring stiffness of the system and the extension of the system. All right, this is for springs in series. Now, what about if you have a case where what about if you have a case where the springs are in parallel, like this? You have the same springs, but you arrange them in parallel. Okay, now in cases where the springs are arranged in parallel, you want to get the new spring constant, you will add them together like you would resistances in series. Okay, so if I tell you right now, your spring constant here is K and K, but because they're arranged in parallel, when you want to add up, you add them like you would resistances in series. So your new spring constant is actually just K plus K, giving you 2K. Okay, so just remember this, that it's always the opposite when it comes to adding springs in series and parallel. It's always the opposite to that of resistances. If you see springs in series, you add it like you would resistances in parallel. If you see springs in parallel, you add it like you would resistances in series. Okay, so now this one is telling you that the new spring constant is actually 2K. It's actually twice the original value. This is actually telling you that your spring is actually much harder to deform. If I give you the same value as before, if I tell you K is 50 Newton per meter, your new spring constant now is 2K, meaning you say it's 2 times 50 is 100 Newton per meter. Much larger than this, right? So this is going to tell you that if you want to get back the same extension of 1 meter, you need to apply more force. Or rather, if you apply the same 50 Newton force as before, you're not going to extend as much. Okay, so it is actually harder now, which would make sense. You know that when you attach springs in parallel, it's actually harder to pull it apart. The reason why it's harder to pull it apart is because the stiffness has increased. All right, so that one is for this. Now, what about the total extension of the spring system? If you're talking about total extension of the spring system, you can try to look at it in this way. If this is force F, this force F is actually being supported by these two loads, these two springs, sorry. So what will happen is that this spring will take F over 2, this spring will take F over 2. The load is split up equally between both springs. And then since this is taking half the force as before, you are going to get an extension of E over 2. This one here you will also get an extension of E over 2, right? Because here you notice that if this one was spring constant K, if I apply a load F, my extension is going to be E, isn't it? That's what this statement actually mentioned. So now if I have half the force as before, I'm going to get half the extension as before. So right now my total extension is actually just E over 2. Okay, I don't really need to add them out one by one. In this case, I add them out one by one because they are arranged in series. They arrange one on top of another. The extensions will add up. But this one, they are not arranged in series. They are arranged side by side. So you cannot just simply add up the extensions together. Here, your total extension is just E over 2. Okay, so this is for this. Okay, then after that, we go to more complicated examples, springs both in series and parallel. So this example here will show you that. I'm just going to clear some of the drawings here. Okay, now for springs that are in series and parallel like this, you would tend to solve it like you would resistances in series and parallel also. Okay, much like what you learned in IGCSE. So like now, what I have here is this. I have 3 springs. This one has spring stiffness K, spring stiffness K, spring stiffness K. Okay, and then I have load F. Okay, so what I want to do is that I want to simplify the system. See, this one can be simplified, right? These are springs connected in parallel. If I have springs that are connected in parallel, what I just need to do is I need to add the spring stiffness together, giving me 2K. It's actually the same as this example here. So this one, the new spring stiffness, if I try to simplify it, it's actually 2K. And then this one still remains at K. Okay. Now, from here, this one is a bit similar to this. These are springs in series. I would need to add them out like I would resistors in parallel. So actually my spring stiffness is actually going to be 1 over 2K plus 1 over K power negative 1, which is this one. So I'm going to get this new spring stiffness, 2K over 3. All right. Okay, then after that, I want to find the extension. Now, the extension, this one, you can just look at this part here. If I want to find the extension, this spring will have a force of F. So my extension is just going to be E. And then this portion here will have a force of F over 2 for each of them. Because the force is half, my extension is therefore going to be half also. So what is my total extension? My total extension is just going to be E plus E over 2. Okay. So my total extension is going to be equals to E plus E over 2, getting me this. This is the extension of my system. All right, so this is one. Okay, then after that, we go on to the last example here. Springs that are both series and parallel again, but this time looks like this for 4 springs. So what can you see from here? Again, this is K, 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 and K. And then you have a load of F. So what you want to do now is that you try to simplify it. What you do is you simplify this one and this one. And this one is similar to this. The two springs that are in series. You want to get the new spring stiffness, you add it like you would springs in parallel. So this one we did it already just now. Your new spring stiffness is going to be K over 2 K over 2. So now this one is similar to this. There are two springs that are in parallel. You add it like you would resistances in series. So this one I purposely left the workings blank. This one, your K prime, the new spring stiffness, is actually going to be K over 2 plus K over 2, giving you just K. All right. So your spring stiffness actually did not change at all. It's pretty pointless to do something like this. Okay. Now, what about the extension? So if you want to talk about the extension, you can do it in a different way also. If I just look at the diagram on the leftmost diagram, which is this one, a force of F. Now, because this is springs in parallel here, this one will take F over 2. This one will also take F over 2. This one will be F over 2. This one will be F over 2. Okay, because you see they are parallel in the first place, the force will be split up between both sides here. And then because this one is in series, this one will be F over 2, this one will be F over 2. So your extension would be E over 2 and E over 2 here. The same goes for this one. This one will be E over 2, this one will also be E over 2. Right, so now as your new extension, it will just be E over 2 plus E over 2 giving you E, right? So no issues here. Now you can actually do it another way also. Rather than basing your analysis on the diagram on the left, you can also base your analysis on the diagram on the right, this one. This one might be easier for you to see. You see, if I tell you that this one is force F, this one will be F over 2. Oh, this one not easier. Right, never mind. Let's not go with this one. This one is not actually easier. Right, just start with this one. This one will be easier for you to see. Okay. I don't want to use that one. Let's not confuse you. Okay, so this is the one that this method is the one that you use to find the spring stiffness of a system as well as the total extension of a system. All right. Okay, so the next two part of the question here will ask you, what's the order of increasing stiffness for this arrangement and what's the order of increasing extension for this arrangement? So increasing stiffness, the four arrangements there are already labeled A, B, C, D. If you say increasing stiffness will be B to D, B to D to C, and then to A. Okay, because B was 0.5 K, D is K, C is 1.5 K, A is 2 K. Okay, this is increasing stiffness. But what about increasing extension? Increasing extension would be something like this. I draw the same thing again. Extension increase. Increasing extension, in order of increasing extension, you get, what's the smallest extension? Smallest extension would be B. Okay. Sorry. In order of increasing extension, that one will be, sorry, what was this? Increasing extension, right? So if you're talking about increasing extension, A, B, C, D, which one is the one? The order increasing extension would be B to D to C to A, because this one you see is 0.5 E, this one is E, this is 1.5 E, and then this is 2E. Okay, so that is what you get. In increasing stiffness, did I? Oh wait, I think stiffness I did it wrongly, right? That's why I was wondering why is this something. I was looking at the wrong thing just now, sorry. In order increasing stiffness, okay, yeah, sorry. The order increasing stiffness is the one that is an issue right now. What's the smallest stiffness here? The smallest stiffness here is BB. What's the smallest stiffness? Smallest stiffness here is actually A. No. Smallest stiffness here is A, right? Or no, 2 over 3 is 0.68. Smallest stiffness here is C. A, B, C, D. Smallest stiffness here is... Nope. Okay. Wait, there's something wrong with this one. The smallest stiffness here is actually B. I keep looking at the wrong thing, sorry. 2K, K over 2, and then K. Sorry, I keep looking at the wrong thing. I'm looking at stiffness. This one is 0.5K. This one is 2K. This one is 0.67K. This one is K. Okay, now this one is easy to see now. So which one is actually the smallest stiffness? The smallest stiffness is actually A. Okay, is A going to C and then going to D and then lastly going to B. Okay, now this is correct. Sorry, I made a mistake just now. This one was 0.5K. This one is 0.67K. D is just K. B is 2K. All right, so this is the correct one. All right, so you see the largest spring stiffness will give you the smallest extension, and then the smallest spring stiffness will give you the largest extension. So in a way, it actually relates to this. F is equals to Kx. If your F is constant, meaning to say you apply the same force, K is actually inversely proportional to X. Okay. K is inversely proportional to X. K increase, X drop. K drop, X increase. Okay, so they have an inverse relation here. All right, so this is the correct one. My mistake, sorry, just now. The stiffness one, I was just looking at the extension. Right, so this is the correct one. So far, so good. Okay, so this one is just talking about the springs.